Hope I'm audible. So, welcome everyone, and thank you for joining us for today's webinar. I am Krishna, and I'm the chairperson of the Women in Engineering Affinity Group of IEEE CUSAT Student Branch. So, the topic of webinar is computer vision, and the session is handled by Sidharth R Menon, third year ECE student of School of Engineering CUSAT. He is a summer research intern at IIT Guwahati, and he is also a computer vision and DL enthusiast. So, just a little before we get started, if you have any questions during the session, please type them into the comment box. I'll bring them up during the session, and we'll also have some time for Q&A session at the end. And please be sure to keep your mics off during the presentation. So now, without further ado, I'll hand over to Siddharth.
Okay, thank you, Krishna. Am I audible?
Yeah,
Yeah, yeah, okay.
Yeah.
So I'll just get into the presentation directly. So is it visible?
yeah,
Yeah, okay. So I would like to talk about computer vision. So if you can describe computer vision in a single statement, then it is just all about recognizing visual patterns. So, computer vision, it is not a term that you haven't heard of before. So it is how the machines like smartphones, robotic systems, how they perceive the world and respond to it. So it is just model. It is similar to human vision, but there are a lot of differences in the processing of the images. So this is all about analyzing images, and we are interested in the spatial information. And mainly, it is all about recognizing visual patterns. There are all a certain type of patterns in the images. So we would like to visualize them, process them, analyze them, and get your result. So, so this is how a computer vision works. So how it is working. So when we think of ourselves, so we see through our eyes and our brain process it, and we'll be able to interpret each images. So it happens instantly. So we have our own sensor, that's our eyes, and we have processing system, that's our brain, and then after processing, we'll get the output. So what the computers do? So computers, they are having artificial sensors. So major sensor that as in computer vision is cameras. So in cameras, again, it takes it converts the 3D world into a 2D picture. That after conversion, it is sent to a interpreting device. So that's mainly a computer, and there is some program or some algorithm running on the computer, and it will interpret the images. So that's it. So I would like to specify some of the applications of computer vision before going into the theory behind it. So the first figure you can see here is it's basically emotion recognition. So emotion recognition, it's pretty obvious. You can see whether the person is angry, happy, sad. It analyzes the facial expressions of the person and get the result. The second image here you can see is the brain. It's actually a MRI scan of a brain. And the green color you can see detects the tumor in the brain. So it is very important in biomedical applications. And recently, even COVID-19 can be predicted using the biomedical image processing of our lungs. And that too is an important application of computer vision. The third one here you can see is it's mainly applied in the self-driving car domain. So it's specifically this is a algorithm called YOLO.
means you only look once. So here what does is that there is a multiple classification and the localization. Here it classifies there are traffic lights, bicycles, car, and where it is located in the given picture. So there are multiple classes here, like it is detecting traffic lights, not only cars, it detects traffic lights and also bicycles. And the fourth one here is it's an application called image caption. So we are inputting a image to the computer, and the computer describes the image after it analyzes the image, and it gives a statement. So first you can see that it's describing a dog is sitting in the hut drawn on sandy beach. So it may not it may not feel it is really pure grammatical. There may be some mistake, but it is much better that it is the computers are able to give this much itself. So it's a bit complex computer vision application. So I would like to talk about how this is done, how the computer vision work. So this is a basic general pipeline of computer vision. So we have some input data. Input data, obviously it's images, or maybe it can be videos. Videos means it's a group of image frames. Then it is pre-processing. So we have some pre-processing, like maybe some changes to remove the noise, or maybe some change in the pixel values or something like that. Then you see selecting the areas of interest, then feature extraction, then prediction. I will get into this with an example. So you can see the example of a facial recognition. You can recognize the emotion. So we have input data, our images, and the pre-processing, which means the noise reduction. There are some noise present, just pre-processing, then color correction, scaling, just enhance the image. Then we are selecting the areas of interest. So for emotion recognition, obviously the area of interest is our face. So we are selecting the face. The face, you can see that the first step is the face detection. And next step is feature extraction. If consider emotions are basically analyzed with the help of our eyes and the position and movement of the eyes, our eyebrows and our lips. So we can see that the extracting the features, these features, you see that it is detecting the eyes, position of the eyes, finding facial markers, mouth, eyes, etc. And then it is making it's into some computer readable, maybe it's turn into numbers, and then it is given to the algorithm and the computer. So computer processes and sees that it is the eyebrows and the mouth is in a particular shape that shows joy or relaxed. So it gives an output that it is the person is relaxed, the person is happy. So let me get to the basics. So computers. So computer images means just a group of numbers. Particularly, you can call it as a matrix of numbers. You can see the image of a car. It's a grayscale image. Grayscale image means it has only one channel. And you can see that X varies from 0 to 639 and Y from 0 to 426. Means that this is the total, there are total number of pixels means 639 multiplied by 426. That is the total number of pixels that present in this image. So here you can see that each image pixel is having some value. So here you can have the pixel values ranging from 0 to 255. So that is the range of pixel value. 0 means pure black and 255 means pure white. So in between there are various pixels that determines the gray color and the other colors. So here you can see that a blue dot is here. So it is at the coordinate 190, 375, and the pixel value is 28. It means it's not, it's closer to black. It's not white, but it's closer to black. And then when we talk about color images, mainly we know about RGB channels. So we have RGB, and combination of this RGB will provide us color images. Means the basic difference between grayscale and color images are RGB has 3 channels, but the other one, grayscale, has only a single channel. So RGB is not the only color space. Color space means we know about a point being represented in a coordinate system. We know about a rectangular coordinate system, cylindrical coordinate system, spherical coordinate system. Each point is represented in various coordinate systems. Similarly, the color is being represented in various color spaces. So we are all familiar with RGB color spaces. So there it is mentioned the color is being represented as a 3D coordinate, we specified a 3D coordinate system, and we have the RGB color space there. So here But for the image processing task, we are not using mainly not using RGB. So we are focusing on HSP color space, and there are other color space too, HLS. So why do we need HSP? So you can see here the image of a balloon. So you can see that it's not, there are some reflections in that. It's not a pure single, it's not a monotonic color. If you're taking its pink balloon, so it's not just a single color. There are some reflections happening. There are some, you can see like some reflection happening. So if you want to isolate this particular image, particular balloon, if you want to, you can isolate it. Maybe you can specify the color of the image. You can take a color picker, click on it, then you can get the color of the image. So you can select all the pixels with having that color value, then we can isolate it. But with RGB, we cannot do that because RGB significantly varies with reflection. So what we use here is HSV color space. So in HSV color space, even though there is channel, the shadow, the H channel will remain constant. So if you are taking the H channel out here for the particular balloon, then we can see that it's same for all the balloon irrespective of the shadow. So it's very easy to mask the other portions and select the particular balloon. So that's one of the applications of HSP. Mainly we are using HSP color space. As our image may not be perfect, there are reflections, for example, for self-driving cars. For example, there are mainly reflections. There are reflections of water on the roads. So all this create problems. So mainly we are using HSP color space. So you can see a day image of a day and night. So in a crude form, how do we classify this? So you know that the white pixels are represent, the white color is 255 and the dark means black means it's 0. So you can see that you can just have a simple analysis of the image. So in night, you can see that most of the pixels are dark. Dark means they are closest to 0. But whereas in the day, you can see that most of the pixels are almost very brighter, it's more closer to 255. So if you can take, take sum of the pixels and take an average of it. Then you're taking each pixel individually and taking an average, sum it and taking an average. Then you can see that the night image has an average very closer to 0 because most of the pixels are dark. But in the day, whereas in the day, most of the pixels are white and closer to 255. If you take the average, then it will be almost closest to it's a pretty higher value. So if you can give a threshold, so if above this average value, then if you're getting there, then you can be classified as a day. Or if the image, average value, average pixel value is less than a particular value, you can keep it as you can take it as a night image. So this is one of a very simple approach to classify the images. So throughout the course, I'm not for talking about the implementation of the image processing task. I'm not getting into the code. I would like to talk the concepts, how it is done, how the technical aspect, how the mathematics is being done. So the basics. So we know about pixels. Now how do we find edges? So before that, what is an edge? So edge means it's a very rapid change in the pixel value between one pixel to another. So here you can see the blue box. It's almost, there is very, very smooth, gradual change in the pixel value, almost mainly same color. But when you take this other one, the pink box, you can see that there are stripes over the dress of the women. You can see the stripes. It's a particular rapid change from white pixels to black pixels. So when there's a rapid change in the intensity. So if you can get a rapid change in the intensity, then it means that there is an edge. And as we have seen in the signals, we classify them to low frequency signals and high frequency signals. Similarly, here you can see that whether the edges are being classified as a high frequency image patterns, and the other one, the low frequency image patterns, they are classified, and the pixels that are not coming in the edges, they are classified as low frequency. So how do we separate this? We need to find the edges. That's the first step that we do in the image processing task. So I already told that it's high frequency image pattern. So how do we separate high frequency components? So obviously we use an high pass filter, but this doesn't look like an high pass filter that we use in our lab. I mean, in the ECE lab, like transistors or capacitor resistors. But rather here we use something called 2D matrix. It's numbers. So I'll get into that. But here you can see an image that's transferred from, this is a image of panda, and after detection of the edge, we can see this is the image, second image. So it's an area where image intensity changes quickly, and obviously those represent the boundaries. And edge detection is one of the primary tasks that we do in the computer vision or image processing task. So convolution is one of the major, very important operation that we do in the computer vision task, and this basics for computer convolutional neural networks. So what we do? So this 2D matrix, that is our high pass filter. So this filter is operated upon the given image, and we get the image like what we see in the right hand side. So how it's, the operation is called convolution, and this, so after operating this filter upon this image, then we will get the edge detected image. So how this convolution exactly works? So I'm getting a closer look into that panda image. So here you can see the pixel values. So, and here are our filter, and we are selecting a particular point, a particular 3x3 matrix over the picture of the panda, and we can see the values, pixel values 120, 140, 120, and so on. And you can see the last row, take it row wise from last row, third row to the first row, we can see a gradual change in the pixels. It's higher in the last final row, then it's turning lower, then again bit lower. Means that the filter, it's turning dark. It's growing, the pixel value is going down. So it means that there is some edge over there. So there is a change in the pixels from white to dark, but it is gradual. There may not be a stronger pixel, stronger edge, but there can be an edge. So how do we do this operation? So here we have the weights, this filter, and the filter is also called kernel, convolutional kernels. So we are operating this upon here, and we have this, we multiply this with each of the pixel values. So 0 multiplied by 120, minus 1 multiplied by 140, so on, and we'll get this value, this 3x3 matrix. And we sum the values. We sum the values and we get a 60. 60 means it's not dark, it's a bit close, it's in between, white or dark between. So it means that there is not a stronger edge over there. And we replace this value, this middle value, this 220, we replace it by 60. And so, and this process is getting repeated. We place this entire box from here, from the top, then we go this, we do this for almost all the pixels. And at the edges, it's difficult to place it over the here, as there are no other pixels over there. So we add zeros to the other edges. Yes, we can add zeros here. Then we can do this operation again. And we'll get, finally, if you do this operation again and again, you will get to see that you will get an image like this. Like here, you can get an image. So this is a high pass filter. So this is also, this high pass filter, the peculiarity is that it detects all the types of edges. So you can see that it is weighted here, the 4, value of 4, and we have negative values here. So these values will be subtracted and this value will be getting added. You can see that. So it means that it is giving preference to this one. But whereas this is another kind of convolutional filter. It detects mainly horizontal edges. You can see that in the last row, it's positive values, then 0, the negative values. There is a change in the values. So if you multiply these values with the pixels over here, you can see a gradual change in the pixel values. Then if you can sum it up, then you can see that definitely you can detect the horizontal edges. So this 2 types of filters that just you can detect horizontal and vertical edges. This one will detect the vertical edges, and XY is detect the horizontal edges. If this is also filters, and there are particular names for that called Sobel filters. These are predefined filters that we can also define our own filters. because all multiple filters, we can have multiple application. Maybe one filter can detect horizontal image out on the edges, maybe other filter can detect vertical edges, and so on. And this is a brain MRI scan, brain image of a brain, and so like the horizontal, the vertical edges are detected in this figure. You can see that here this region does not have any vertical edge. Here the horizontal edges are detected. You can see that horizontal edges are detected. So we are operating upon the one filter for vertical edge detection, other filter for horizontal edge detection. That is what happened here. Okay, so we have talked about high pass filters. So where do we use low pass filters? So low pass filters are mainly used for removing the noise from an image. All these tasks comes under using of the low pass filter. Mainly we are using for pre-processing of image. We extract the image from a camera, then we do some pre-processing tasks. Maybe it's I already told about taking out the noise contents from image. So mainly low pass filters are used for that. Same convolution operators, and the filter metrics will change. There are another kind of filters available. And here we can see that this is the image. We have edge detection over here with the convolutional high pass filters. And but here you can see that these are noise. High pass filters always amplifies the noise. So you can see the here noise. So we need to get rid of this noise. So for that we use low pass filters. So we use low pass filters after we process the low pass image by low pass filter. Then we give it to a high pass filter. Then we can get the little more better edge detection. Over here, you can see the noise have been reduced. So this is one kind of low pass filter. It's called Gaussian blur. I would recommend if you want to mention some names. So I'll be talking about a lot of names here. If you want to go to more details about this, you can just mention those names. Just note down those names, and you can refer to them later. As this computer vision is a vast topic, so I should crunch this into a 1 hour session. So I can't go much deeper into the topics. So at least you will get familiar with what is happening here. So here, this is the predefined filter, and it's called Gaussian blur. And this filter, same as we see for the high pass filter, this is also operating upon the image like a convolution. That operation is being done, and you will get a low pass filter image. And here you are multiplying with 1/60 as the sum of this convolution filters as 1/60. So we need to have a normalization. So we multiply by 1/16 over there. I'll get into it later. So this is one of the most popular edge detection algorithms. So we have seen that for edge detection, we have to use a low pass filter first, then a high pass filter, and we'll get an edge detection. So this is an algorithm which includes all these. So you can see that it filters noise out using low pass filters. Then edges have been detected using high pass filters, and we apply some isolate the strongest edges to get a more enhanced edge detection. We apply something called non-maximum suppression. So if you can use these algorithms, and you can get an image, you can easily detect an image, edges from an image. So mainly these things have been implemented in Python, and there is a very popular library called OpenCV in Python. So OpenCV stands for Open Computer Vision. So there are lots of functions available to carry out these processing. So there is a function called canny, and if you can give the image to this function, then the function will return a edge detector image. So you don't need to know all these steps that are happening. So just use the OpenCV function, OpenCV library, and use the function, and you can get it. So I would like to take an example of how in the perspective of self-driving cars, how the lanes have been detected. So you can see this is an image what the camera in front of a car sees, and you can see the lanes have been detected here. So how do we do that? So the first step, obviously, we are almost doing our processing in the grayscale domain. So even in OpenCV, there are functions to convert from RGB channel to the grayscale channel. We can convert a color image to a grayscale. So first we are converting to grayscale. Then we apply canny edge detection. You can see that you'll get an edge detected image. So even though these are edges, so the basic idea what we use here is that the lanes are in straight lines. That is the assumption that we are doing. So we are going to detect lines in the edge detected image. Here you can see that even though these are edge detected, these lines are not continuous. If you zoom in, these are not continuous. There are breaks in between. So we need to have a continuous line detected. So for that, we use something called Hauff transform. So it's basically very simple. So we know that equation of line is y equal to mx plus b. So this is an image space. So it's a line in xy coordinate system. So with MB as the in Hauff space, we are transforming this from image space to Hauff space. So here you can see that we have a point. Point means H line is transferred to Hauff space with help by converting into a point, as we have seen. So it is mainly basically the slope of the line with the intercept. So we are taking it. So we know that each line have a particular slope and a intercept. So when it comes to the Hauff space, we can see it's basically slope versus slope and the intercept. So you can see that it's just merely a point. So we have two lines over here. So in Hauff space, that will be 2 points. Then same, we have two lines parallelly over here. So it will be almost, parallel. Here we can have the slopes are same. Slope are same means you will get an image like this. D will be the answer. So the slopes are same. You can see that here slopes are, C will be the answer. Slopes are M is slope and B is intercept. So slopes are same here. And you can see these will be the 2 points over in the Hauff space. Now, if you are taking a reverse, you consider a point in image space, then definitely we'll get an line in the Hauff space. This will be the answer. You can check it for yourself. You know the y equal to mx plus b. And if you are taking b, y minus mx equal to p. So if you are taking a point in the image space, definitely you'll get a line in the Hauff space. So if you are taking 2 points in the image space, then what happens? So 2 points in image space means we have a intersection in the Hauff space. So this is very important concept as far we are concerned. So we have points in image space. For detecting straight lines, only we have points. So if we have points like this, and we are taking points, and if we see that we can find a intersection over the Hauff space, then we can detect that there is a line passing through these 2 points. So that you can see here, we have in the Hauff space, we have 2 lines over intersecting point over here. That means that in the image space we have detected a line passing through these 2 lines are in the image space. These are points, and you can see that these 2 points are being passed through a straight line. So that means this is the principle that we use to detect lines in the original image. So if we can find intersection, we are taking all the points from the image. Then we apply this, how we converting everything into Hauff space. So wherever we can find some intersection over Hauff space, we see that there is a line that is being detected in the image space. So this is the basic principle. Same. Yeah, you can see the very large number of intersections. That means you can detect a line over the image space. So, but there's a big problem over here. If you are doing this, consider we are having 90-degree slopes. So it does not work out if the slopes are having, if the lines are vertical, it having infinite slope. So that's not possible. So we are not taking in a MB form, but we are converting into a polar coordinate system. So in polar coordinate, just like the same other one, we have having sinusoids over here. Just the intersection of sinusoids will give the line. So after doing the Hauff transform, it may look like this. So, but it will detect almost all the lines. So there is further processing of this image should be done, and you see that we should avoid these regions because our lanes are only here. So actually, what we are doing is that we are masking this region, this particular region, because we are making another assumption here. The lanes are only occurring the lower half of the image. It's like a trapezoid shape, like a trapezoid here, like this. So we are masking that place and getting rid of all the other region. Then we can detect the lane. And you may see that this is not that perfect. There are some broken parts over here. This because there are a little bit of more math involved in this Hauff transform. and there are many other parameters that need to be defined by us. So proper tuning of these parameters will definitely yield a very good, perfect line, as we have seen in the early case. So you can do this in the OpenCV with help of OpenCV. There you specify the parameters, and you can change in the perfect tuning of the parameters will lead very good results. So the other lane detection, sadly, that is not gonna work for a real self-driving car. The major problem with that is we are assuming that the roads are straight lines, the lanes are straight lines. But you know that there are curves, there are bends. So when there is a curve, obviously that line principle won't work there. So it's so we need to consider some more in using some advanced techniques over there. So before going to the, let me tell, so why do we need to detect the lanes? So in the application of the for the self-driving cars, the lane is being mainly detected for how much steering angle that the car has to turn. So if you can find a curve, if you can get the how much angle of curvature of the curve, definitely you can see that how much our steering angle should be turned and how much degree of angle should specify for the car to turn. So yeah, so if we are getting a bird's eye view of the lane, then definitely we can find the curvature of the road. So that we are using like perspective transform is a method that is used to get a bird's eye view from this is the left side. You can see the image that is being seen by the camera in front of the self-driving car, and we are transforming this image to a bird's eye view. So you might have already learned up in graphics in our college that perspective image, something like that. So basically that is what we are doing here. Some transforming, we are specifying a few points over here. We are specifying the few points and being transformed into this this view, and using some coordinate system, using some mathematics involved in that. So if you are getting this, then definitely you can get the curvature. So this is what, after doing all the edge detection, all those tasks, then you are getting this. I'm not going to the detail of this, it's a bit complicated. So you can see that the lanes have been detected. This is the left lane, right lane. And we are, see, after a few more processing, you can get the direct images over here. We have detected the lanes completely from a bird's eye view, from an image from a camera that is that for sees in the only just from the front view of the car. And what we do here is fitting the curve into a polynomial. So we are fitting the curve. If we can fit a curve into a polynomial, definitely there are equations to find the curvature, the angle of curvature of this polynomial. So this is the coefficients doing with there are techniques to find the coefficients, and if you can fit them, there are other equations to find the curvature, find the angle of curvature. So we have found out the angle of curvature from the image, but this angle of curvature, this angle is not directly exact as the angle that we need to steer the car. As this is from image, the other one is real world. So there are again few more techniques that you should do to convert that angle to the steering angle, and it is related. There are some other methods too. So next, something I would like to talk is about HARP features. So it's basically for face detection. So we have face, these are the filters itself, and the HARP features are mainly, so if you take a human face, so we can see a lot of places where the pixel densities changes very intensely. So above the eyebrows, our eyes, our lips, all these places are, you can see that there are changes, significant rapid changes in the pixels. So we used to detect those things. So for those features to detect, we should have some appropriate filters for that. So those filters, we are seeing these filters detected edges, lines, rectangular patterns. So these are called HARP features. So what this this is actually a machine learning algorithm which is called HARP cascade classifiers. So we have seen what is HARP features. So what is cascade and what is classifiers? So how this algorithm work? This is image, and this image is being processed with this filter. So here it detects particular lines. So it here you can see the background, there are no lines. So that portion is being avoided by, and then it is only detecting this only the person's face with the body. So the rest of the portions have been neglected after we apply this filter. So after that, we will get this image, only the image, no backgrounds. Then again, we apply something, some other filters, some called rectangular feature detection filters. So after applying this, then her body is also gone. So we finally it is constrained to the face, just the face. So this way, if we apply further, again, then we can see that it's detecting a face. The other regions have been classified as not face, and those are avoided. And finally, we'll get something, detect something called face. Then we can see that a face is being detected. So this is machine learning because you have to train the classifier. The classifier means it classifies whether it is a face or not face. So mainly it is they're using some machine learning techniques, like maybe it can be also neural networks too. So with the help of this, you can you'll be training your network with a lot of other images, lot of faces images, lot of non-faces images, and that classifier will train so that it will be able to detect the images. So then how to extract the features? One of the major other steps you have seen the earlier when I described the pipeline is that you have seen that the images have been there is a step called feature extraction. From the face, you extract the features like eyes, our eyebrows for emotion detection, the position of the eyebrows, our lips. All these features are extracted. So how do we do that? So for example, consider this picture of a mountain. So if you want to detect a mountain from an image, mainly object detection. So here we are making assumptions that mountains are in the shape of trapezoids. So we need to fix something called a trapezoid over here. So these are green dots are corners. There are various algorithms for detecting corners. Corners can be some features of the mountains too. So one of them we are dividing the pixel and we are finding the gradients values plus the direction of gradients. So and we are breaking down into a grid form, and grid form is converted into a single vector shape, and you can see that this is one kind of vector. It can detect this shape from an image, and this is another kind of vector over here. You can see that circular this one, if we break down into the vector form with the gradients being, these are gradient directions of the gradients, you can see. So this you will get into a one-dimensional vector over here. So these are called feature vectors. You can if you have this and compare with the original image, if you can find some similarity over there, then you can see that this object is being detected. But this is far too not that much applicable, as we know this is all the mountains are not in this perfect shape of this, so can introduce some errors. But these are some of the features. Gradients are very popular main features that are included in the images, and it is one of the major feature vectors too. So feature detection is very important. What if we have to detect for in the terms of self-driving cars, what if we have to detect pedestrians or other vehicles from the road? So this should happen in the real time. Our algorithm should be very fast to detect the features and to classify that image, that object as a pedestrian or other car vehicles. So it should be time is very critical for this application. So I would like to discuss one algorithm that is very fast and very that works in very real time too. So that it's called OR. OR means oriented fast and rotated brief. It contains two algorithms inside that. So key points are the points. So we have pixels in our image. So if you want, so how do we classify whether which pixel is important for us to construct a feature vector? What pixels should be considered? So all that pixels that we are considering is called key points. So these are points where there are significant changes in the pixel values, sharp change from light to dark or dark to light. So these points are happening. Here you can see that from the image of a cat, the main points are around his eyes, nose. These are the interface. You can see the key points. There are multiple key points. Key points are being detected by this circular shape. So you can see the key points over there. So how do this work? So we have original image. So we have something called key points. So how does the computer analyze these key points? Just detecting the key points one, how do we fed this into the computer? So the algorithm converts each key point into a vector. And these are called, so each vector will be unique for each key points. Each vector corresponds to each key points out in the face. So these are in binary. So binary is very efficient for the computer to do processing with. That's why it's very fast. That's why this method is pretty works in real time. So you see that this is a kind of face detection over here. You see here there's a face of the woman, and the key points are already fed, and we find the key points and converted into feature vectors, and then we are given this entire image. Then we can see that then we are analyzing this image. So computer already knows the key point, the feature vectors of this girl, this woman, and how her face looks like. So that is described by that feature vector. So then it checks whether this feature vectors can see anywhere on this image. So it finds out that here, this portion, after analyzing this entire image, it finds that here, this region, it corresponds to this, because their feature vectors are almost equal. There may not be all the features matching equally, but there may almost all the features will match. So you can keep a threshold whether this much key points are matching with that particular object. Then you can see that it has detected an object or a face. So that's basically what is happening over here. So one of the so I have told about OR is oriented, fast, and rotated brief. So fast algorithm will find the key points from a particular image. Then that key points are converted into feature vectors using the brief algorithm. So that is what happening here. So this is one kind of feature extraction step. So we have seen that it is a feature. They're extracting the features from image, and then they're using to compare for similar kinds, such as similar images like faces or any other objects. So next I would like to talk about deep learning. So deep learning is all must have heard about deep learning. So deep learning has a very powerful application in computer vision. So basically, when you talk about computer vision is not an AI. It's not an artificial intelligence, because it's purely image processing, just using some metrics and making that. Only the half feature is something machine learning problems. But all other things that I have discussed till now, even the lane detection, those are not included in using any deep learning techniques, purely mathematical and basic image processing tasks. But deep learning has very significant application in computer vision. So why deep learning? We have started to hear deep learning in the few years, but this deep learning, it mainly talks about neural networks. But this neural networks was introduced way beyond in the 1950s. But we are starting to hear this in the recent times. So why is that? So there are multiple reasons for that. One of the major reason is the shortage of data in that earlier time. So we have internet right now. So it's not difficult. Suppose we want to create a classifier. We want to detect, build an algorithm that classifies whether it's a cat or a dog. So if you can get a lot of images of cats, a lot of images of a dog, then you can train the network with the help of these images. And then the computer, it will learn about if it sees a new image, it can identify whether it is a cat or dog. So neural networks are pretty data hungry. So large amount of data is required. In the older time, there were not that much data available. So with the coming up of internet, so we can get a large amount of data set, and it is making the deep learning taking off. The other thing is that deep learning requires a lot of computational power. So The CPUs, as we have seen, is generic purpose processors. They cannot do. It will take a lot of computational power to train the network and classify, work in real time. All this takes a lot. Maybe training of the network may take weeks or even months. But you can see that with the coming up of GPUs, GPU graphic processing units, the deep learning training with the coming up of faster processors, the training time has significantly reduced. And deep learning training is a pretty iterative process. So in GPUs, you have something called, there are various architectural advantages that it can provide over the CPU so that it can help deep learning take off. So those are the things that help deep learning to taking off. But let me talk about how deep learning is applied to computer vision tasks. So this is a symbol. Deep learning, obviously, it is about neural networks. So what is a neural networks? So here, this is a simple neural network. You have an input, you have a hidden layer, you have an output. So I'm focusing on a particular neuron. A particular neuron is enlarged over here. So we have some mathematical operation happening here. We have these are inputs. These are numbers. So these are weights, W1, W2, W3, W4. And here some operation, just multiplying this weight with the inputs and summing up, then adding another term called bias. And we are doing this mathematical operation inside the neuron. And then we are having maybe some activation function, we can call it as a threshold. Maybe above this, it classifies as something, maybe cat, or if its value is less than 0, it's classified a dog. Maybe 1 means, if you're talking about a dog, cat classifier, maybe if you're getting a value of 1, it means dog, or 0, it means cat. This is a very crude explanation. So I'm not going into much detail of the neural networks. So for neural network, we are describing a error function. So this network learns from errors. So training process, there is an error function. So the training process happens for reducing this error function to its max minimum. So these W1, W2, W3, W4, these are unknown in the initial, before training. So after training, after seeing a lot of cat, dog images, the network itself calculates this W1, W2, W3, W4 to an optimum value with various optimization techniques. And then if it sees something new images, new cat images, new dog images, then definitely it can classify again. If it sees a new image, definitely it can classify accurately. So we need to reduce this error function. So that is that technique is called gradient descent. So I'm not going into much detail here. You can refer. You can just search gradient descent, and definitely you can see how it is being done. So I would like to mainly focus on computer vision rather than deep learning. So this is the equation of error function. So with various equations, you can reduce this error function. Like this, like here, you should reduce the error function to minimum. That's what is describing in this figure. So that is how the errors are reduced with a technique called backpropagation. Backpropagation just means that initially when first, let's talk about an untrained neural network. So if you are having an untrained neural network, definitely it cannot identify a cat or dog. So suppose I'm giving an image of a dog. So it sees that that image is going through here, and the weights are not initialized, but we somehow let it be randomly initialized, the weights. So it will calculate something and it will output something. So if it is classified as a dog or cat, the image is dog, then we are getting an output cat. It's obviously wrong. It has made an error. So we are propagating this error backwards. This error is being we are sure that we made some error. And this error is being propagated backwards, so that parameters W1, W2, W3, extra defines the network. So this error is propagated from the last layer to the initial first layer, and the weights are being updated. So there are a lot of equations involved in this. So this is the basic basic thing happening here. That is called backpropagation. In the initial step, we are giving a training image, then it is forward propagation, and it gives an output. Output may or may not be right, and if it is wrong, then you are taking that wrong value. We are calculating how much error is there, then we are taking it backwards. So that backward operation will alter the parameters of the network, and after doing a lot of with help of lot of images, then definitely you will get an optimum value for the W1, W2, W3, those parameters. So that is how a neural network trains. So it is has a lot of math involved. Deep learning, computer vision all have a lot of math. But if you are using some Python libraries like OpenCV, for deep learning you are mainly using PyTorch or TensorFlow. So these are some kind of neural network deep learning libraries or frameworks that help us to. It's pretty easy to do these mathematical operations. So you can just call a function. So you don't need to know the math behind all this. Just get to know that you just give the suitable parameters for the function. Then you can get the trained network. So these are called deep neural networks. Here you can see it. Multiple here there are only single image, single neuron between single hidden layer. If you have multiple hidden layers, then it's called deep neural network. So here I have an image of cat. So my cat, it's a 2D image, but here it accepts only a single value. So we are converting this 2D matrix of pixels into we are converting into a vector, single 1D vector. So you can see its pixels value ranges from 0 to 255. Here you can consider grayscale image. So we are normalizing it here. So neural net, there are a lot of optimization techniques or pre-processing techniques that are to be done before feeding some data into a neural network. So one of the things that is required is normalization. So here these are pretty large values, 0 to 255. It's very big values. So we need to reduce that values to some standardized between 0 and 1. So I'm dividing each pixel value by 255. So definitely I'll get the input values from 0 to 1, in between 0 to 1. So I'm giving this. And I'm giving, so these are just numbers. And this has been analyzed, this numbers being calculated due to that with the mathematical operation. Then finally it detects that this cat. 0.98% of the neural network is saying that the particular image is a cat. So this is a typical example. But the deep neural networks has got a big problem with for computer vision. As here we are not preserving the spatial qualities of the image. You see the image is just broken down into a one-dimensional vector over here. So these are just numbers. These numbers. So it does not preserve the spatial it does not preserve the spatial parameters of the image. So you can see a dog image of a dog over here. So I'm talking about the disadvantage of the previous network that you have seen. If the dog was here, but if you see the dog was in middle, so if you see the dog was in this side, the left side, or whether it was in the right side, all this create problem to the neural network. Maybe it won't identify this as a dog because it's not having a spatial representation, because we are giving just numbers to the network. So we can avoid this with the help of something called convolutional neural networks. So convolutional neural networks, it basically, I have told earlier about the convolutional kernels filters that we use for edge detection. So it contains a series of layers. Here we are giving the input image directly. We are not converting into a single dimensional vector. We are giving the image directly. And these are called convolutional layers. And we are having multiple convolutional filters over there. These filters, maybe one filter is for detecting horizontal edges. Maybe one filter will detect vertical edges, and so on. So that's what here. So there are other layer called pooling layers, and then you'll get feature map. Then you are converting into fully connected layer, and then you will get an output same as the other one. I'll get in this detail of this. So convolutional layers, you already know about that. Then how the second, after convolution, we have another layer, max pooling layer. So how does it work? So we have a 2 by 2. We are after convolutional filter application, then you will get something like this. Again, you will get metrics. So here you can see that we are doing a 2x2 max pool. It means that we are converting it to a 2x2 matrix over the output of the convolutional layer. And output of the convolutional layer is called feature map. So here you are converting into 2x2 matrix, and max pooling means you are selecting the maximum value of first 2x2 matrix. So here maximum is 20. We are taking in 20 here. We are taking here maximum is 30. We are taking here. The maximum is 112 and 37 here. So we are reducing this pixel. So you can see here that the input image is 100 by 100 pixel. We are further reducing it to as it passes through each of these layers. The size of the input images reduces, and extracting the features happen automatically in convolutional neural networks, which is a very big advantage. The other way, we use various techniques to extract the features from an image, like eyes, nose. If you want to describe a human being, it should detect whether it has eyes, it has nose, it has lips, it has ears. If you can detect all these things, you can classify it as a human. If these eyes, nose, ears looks like that of a human during its training process. So what is happening is that we are getting finally a feature vector over here. So this happens automatically during the training process, and complex nonlinear features have been described in each of these convolutional layers as the image passes through these networks. So that is one of the major advantage of convolutional neural networks in computer vision. So it reduces the feature extraction part because it will do it automatically. It's called like so you don't need to do some other preprocessing. It can increase the speed of the processing, and it's very important for real-time applications using convolutional neural networks. So this is visualizing. How does this output of the CNN, how does it detect the images? So this is, here you can see layer one. Layer one, how after application of the filter, you can see that you can see here vertical edges. So it is detecting vertical, it's my 45-degree angle edges over here. So it is in the first layer, it is detecting edges, just edges. When it comes to second layer, this is the image that we are feeding. So you can see here it is detecting much more complex features, but it's not, you cannot distinguish between each other. But you see that there is something else is happening, because other convolutional layer, we have a convolutional layer, then a pooling layer, then again a convolutional layer. The first convolutional layer extract the features from the original image. Then the second convolutional layer extract the features from the previous convolutional layer. So it becomes more complex. More complex features are being extracted through the network. So when we consider layer 3, we can see it detects again complex patterns. Again, pattern recognition takes place. You can see that it's detecting something called here. You can see it's detecting something called like our face, like a human being can do. When we get again, when we go to layer 5, the final layer, maybe you see detecting eyes. You can see that size is given. You can detect eyes. See the faces. You have the faces. It's pretty complex, very complex feature to detect the face as it is. But the neural networks do it by themselves through these various convolutional layers. So that is what basically happened here. So this is the overall step over here. You are actually downsampling the image. You are converting the very high pixel images to very small pixel values after taking. Why do we do max pooling? Max pooling we are mainly doing for taking the very significant parts of the pixel. You only interested the features that are significantly detected by the convolutional layers. For that, we are using the max pooling layers. The convolution layer, max pooling layer, convolution layer, max pooling layer. So we have a series of convolution layer, max pooling layers over there. So this is how image flow through a neural network. And finally, we have something we have already seen, deep neural networks. We will have some feature map. This is a feature vector, and we are feeding this feature vector into a deep neural networks with normal neurons, and we'll get an output. So that is what happening basically in the convolutional neural networks. So this is one of the major problem with convolutional neural networks. It's called Picasso problem. So this is obviously it's a phase, but here it's not a phase, event phase. But the convolutional neural network detects predicts that both these are human faces. It's because it's not the problem. Again, there's a disadvantage with convolutional neural networks. So it detects complex patterns like eyes, nose, lips, but it does not preserve the spatial relationship between these. Where, with respect to eyes, where should the nose be located? But it won't check that. It will check that whether there is an eyes or nose and the lips on the images, but it won't check the relationship between these features. So that is one of the major problem with convolutional neural. So you can fool a convolutional network just giving the input like this. So there are other network like capsule neural network, CapNets, that is used for avoiding this problem. That's again some advantage. This goes on. And again there are networks like recurrent neural networks. For again the recurrent neural network image caption I have already shown earlier. It uses both convolutional neural network and recurrent neural network. So recurrent neural network is something like it has some memory in it. So consider I have to do some gesture recognition. Maybe I'm given a video of a person running, or maybe a person walking. So how do I recognize whether a person is running or a person is walking? So we should not analyze a single image. We should analyze the previous image, previous pixel frames also. So we should remember the other previous frames also to analyze whether it is a walking or running. So for that, we should have some memory. We should remember the past. Like we in electronics, we know about sequential network. Same thing in software. It's happening in this neural network. That's recurrent neural network. So it's again another classification of neural networks. It's also used in a natural language processing. It's a bit more advanced than convolutional neural networks. So this is something class. I'm not going to detail. I'm winding up right now. So this is pretty again little bit of advanced level. So classification plus localization. We are classifying this as a cat, but we don't know where the cat is located. I have a cat in this image, but I don't know where is this. So this algorithm will again give me the location of the cat by specifying the center point of the cat and also the height and width of the post cat in that image. So that is classification and localization. The other one I have already shown you, the self-driving car recognizing the pedestrians and the other vehicles. That is using this method. Classification, we have classification over there. But if you have seen a pedestrian, we have classified that there is a pedestrian over there. But we need to detect where the pedestrian is in that particular image. So we use technique called localization. So this is that algorithm. It's pretty complicated. There is not enough time to explain this. So you can always look into that. So this is what's happening over there. So I would like to give you some resources that I use to get more detail about this convolutional neural network. So this guy over here, he's Andre Karpathy. He's one of the famous computer scientists all over the world. And he is the director of AI of autopilot in Tesla. And here you can see this is Fefeli. Fefeli is also a computer scientist. She is director of Human Center AI in Stanford. So they offer a course at Stanford. It's called CS231N Stanford. And the name of the course is Convolutional Neural Networks for Visual Recognition. So the videos are available in YouTube. You can just search CS231N and then you will get all the videos. So they explained it very beautifully about all the concepts, including from the basic beginning to how convolutional neural networks are happening, or how neural networks are working over there, then how recurrent neural networks are applied there. Then again for the how from basics to the advanced level. So again, other sources are one obviously Andrew Coursera courses. I think that most of you are doing that during this time, and it is one of the popular courses which helps you learn more about deep learning. And also there are other videos with this is from MIT. There's a course like Introduction to Deep Learning. It's from Alexander Menon. So all these videos are available for free. These videos, and again Lex Friedman deep learning lectures, all these are available in YouTube. You can just search for this videos, then definitely you can get it and watch it. So these are these are really good sources for using to know more about this deep learning, know more about how, because this course is CS 231 is focusing just on visual recognition, not on generic deep learning, how convolutional neural networks are using for visual recognition. That's what this is focusing on. And then when we come to the software part, we are using various libraries. Mostly the programming language that is used for deep learning and computer vision tasks is Python. So we have a lot of libraries, a lot of packages available in Python for deep learning and computer vision tasks. OpenCV is for computer vision tasks, and this is Keras, this is TensorFlow, this is PyTorch. These are the different types of libraries that are available for deep learning frameworks. So I told about training of the network, back propagation, forward propagation. All these are just functions over here. You can just call the function, you can get a network trained. So it's pretty easy. TensorFlow is developed by Google Brain. PyTorch is developed by Facebook AI. And you can choose any of them. Both have advantages and disadvantages. Both functionality of both are different too. So can get to more detail. You can get to know more about these from YouTube. There are videos and from their documentation itself. And Andrew Ng's deep learning course is using TensorFlow. So and Keras too. Keras actually works on top of TensorFlow. TensorFlow is a low-level API, and Keras is a high-level API. Using Keras is pretty more simpler than using TensorFlow, but backend is always TensorFlow. Right? So that's it. I hope you get to know a little bit about, at least you are familiarized with deep learning and computer vision. Thank you. Thanks a lot. Thanks a lot for listening.
Thank you, Sidharth. It was a wonderful session. So we can go for a Q&A session. You can type the questions into the comment box, or you may ask him directly.
Yeah, hi Sidharth. Rajesh here. Am I audible?
Yeah, you're audible.
Sidharth. So that's a really nice presentation.
Yeah, thank you. Thanks a lot.
You have talked about the mainly image recognition and yeah, moreover, roaming around the images only. So I have a question regarding the text extraction. Okay, so if suppose we have to extract the text from that image.
I can't clear you properly.
Oh, yeah. Okay, so what my question is that if suppose you have to extract the text from an image, okay, you have some receipt image of a receipt, and you have to extract all the who is buyer, who is purchasing, from where it has come, those things. So what's the approach? What is the approach for that?
For extracting text, we are mainly using recurrent neural networks. It's NLP. I am not that familiarized with NLP.
Okay.
So I would like to stick with computer vision itself. So it's a pretty vast topic. I don't want to go more to the other field.
Okay. So fine. That's fine. So another is like two types of image recognition we have seen today, if I'm not wrong. One is definitely we are training a model, like you have said cat and dog, right? We have to train the model, and then it will able to identify that image, right?
Yeah.
Another is if we have to compare two images, right? There we don't need any training, right?
Compare
two images. You can, if you have. Can you just elaborate that? How do you?
Yeah. Okay. Suppose I have given you a normal image of a phone, and another image would be like it's distorted. I mean to say, it's one phone which somehow it has the phone has been distorted. Okay. So now we have to are we able to find that both images are belonging to from the same phone?
Yeah, possibly, but distortion can be corrected. I'm talking about. So for example, in the self-driving car perspective, the camera's images are distorted. The images that are taken by the camera. So there are techniques. Even there are functions in the OpenCV, so you can change this distorted into undistorted. So if you can do that, then you can definitely compare the pixels between these two images, then you can obviously detect that whether it is right or they are similar or not.
Oh yeah, exactly. I'm just asking questions from the business perspective. Like you have a phone and it has been broken. Next time again, that has been broken on top of that, like a couple of times, and you have to find that this is the same thing happened on the previous image or whatever previous time it has been done. So that we're able to identify that, right?
Yeah, definitely. If you have some training images like how the phone is broken, whether the display is wrong, if you have some images like display is broken, then if you are training the images, training the network with that images, then it can definitely identify that it is a broken glass or something like that.
So
So
to compare two images, that there also we need training.
we cannot, but comparison means you should at least to know how the glass is broken, right? If you are you're making some particular model of a phone, and if you are having some examples of how the glass phone is broken, if you are
Mm-hmm.
having some, so it has some memory of this, the network has some memory of how it is being broken, what is broken there. So if you have some images, definitely you need to have training to get this, identify what kind of
Okay.
problem it is with the phone.
Okay, you
So
mean this the few sample images of the original, uh, you know, that phone. If suppose we are taking a phone as an object, right? To
yeah,
train that how actually phone that looks, and then
yeah,
we'll see a
yeah, you need to,
long,
I
right?
guess so.
Yeah. Okay. Cool. Thank you.
Going through the chat box. Oh, is the reduction or expansion of convolutional ANN is like the encoding and decoding in digital electronics? It's not similar. Just the digital electronics, you have an analogy only in recurrent neural networks, I think. And here in convolutional neural networks, what we have seen is just getting this, downsampling these images. So we have a big pixel of images, we are reducing again further, we are extracting the features and reducing it further, we are decoding, encoding it, so that finally we'll get a vector which has the feature detected data available. So that is encoding. We use decoding also in convolutional neural networks, such as transpose convolution. There is something called transpose convolution. It upsamples the images from that encoder part, then it will upsamples the images. So that is mainly applied in image reconstruction applications. So that is, there are also, and there's also called something called auto encoder available in this deep learning, and that uses a combination of encoder and decoder, and uses this of things. So there's also something called fully convolutional layers. So fully convolutional layers also have something called is also have an encoder and decoder. It is mainly for semantic segmentation. You can search, you can see semantic segmentation images. It's mainly for self-driving cars, how to identify the particular points, particular image as a wall. Instead of throwing a bounding box, it will detect the entire human with the detection. You can see, you can just search it and you can get it. So how did you manage to get an IIT internship in your second year? Uh, if you have some, if you have enough CGPA along uh, with you have some interest, or you cannot just say you have an interest in something. You should at least do something. What I did was a little bit of NPTEL courses on digital electronics and some analog electronics. So I did a little bit on that, and you should always go out of your textbook. So if you're learning something extra, then you will get to know what you are interested in. Definitely you will know what is happening around. You should just read something extra. You should read blogs. One of the main blog that I use is Medium. You can search Medium. It's one of the technical blog. You can, if you have any doubt, you can just search there. It's not only in the CS perspective, for everyone. Has whatever you are interested in, you can search there and you will get to know more about that. And then other one is there's Kaggle. So for us
in this, there are various competitions happening in Kaggle. So there you get to apply this convolutional neural networks, these deep learning tasks. So you can do it. So it's, if you have a will to do, then definitely you can secure an internship. Yeah, you can do it. So any more questions?
Are there any more questions? I think we are over with the questions. So thank you, Sidharth, for sharing your knowledge and giving a wonderful session. So and I would like to thank all the participants who have attended this session. And before wrapping up, Sidharth, do you have anything else to share?
Yeah, nothing. Yeah, stay safe. That's it.
Yeah.
Thank you.
Okay, I think we can wrap up this session. Thank you all.
Thank you. Thanks a lot.
Great job, Sidharth.
Yeah, thank you. Thank you. Thanks a lot. Bye.
Thanks a lot.